for it to be a right-handed coordinate system. It is indeed a right-hand rule. So, in a right-handed coordinate system, I cross j equals k. You put your hand in the direction of the first vector, I, so I've got basically 360 degrees of freedom there, but my fingers are pointing upwards. I want it so that when my fingers bend, they bend towards the second vector, the j.
Yeah.
So the only way I can do that is my hand to be pointing up like this, my fingers point towards j, my thumb points in the direction of the resultant, or the result. So that's why k has to go into the board. By this, if I do j cross I comes out of the board, so j cross I is negative k. Notice that if I just switch the order in which I'm multiplying, I get the negative of the answer. Commutative property does not hold. The order does matter. If I do j cross k, well, j is pointing in that direction. K is pointing into the board, so j cross k is I. K cross I is
J.
K is into the board, I is up, my thumb points to the right. If your thumb points really far back, it still does not change the direction. Your abnormalities in your hand do not force mathematics a different way. This is just a trick. So notice there that I cross j is k, going in alphabetical order there, and then going around the corner, ij. J cross k is I, k cross I is j. So as long as I'm going in this direction, I get a positive result. If I go backwards, so k cross j is negative I cross k is negative j cross I is negative k. So it's positive if I'm going to the right, negative if I'm going to the left. So given that convention right there, what is the direction of the angular velocity? Assuming I can hold it steady. Amy, you did the first part. Not willing to commit.
I don't blame it. It just confuses me figuring that out.
All right, which way is it spinning? All right, so I got my axis is vertical here. So that means my thumb is pointing up or down. So which way, so both of you are having, I've got a couple people doing the thumbs up here, because it's spinning around like that,
Yes.
about the axis. My thumb is pointing up, it's pointing in the I direction, or I hat direction.
And that's based on your thumb?
Yeah,
Okay.
the thumb points in the direction of the vector.
That'd be K. That'd be K.
Close.
K hat.
I wasn't picking on that yet.
Negative K.
Negative K. Because it's spinning around like this, so spinning around like that, my thumb points to the back of the room. And I had K being positive going that way. So if I close that door over there, what would be the direction of the angular velocity? All right,
Big I.
it would be right-hand rule.
Yeah, I did it left-handed, didn't I? Because I'm left-handed.
Yeah, the left-handed students,
Yeah.
you have to just either remember it's the other hand, or some left-handed students do the left-hand rule and then their answer is the opposite, whether they come up with their left hand. Which works fine until they start getting an intuitive sense, and then it all gets scrambled up, and then they come out the other end, either broken or better.
Broken.
So left-handed, given your age, were you taught to write like this? Okay, you had a more experienced teacher then?
Yeah, my mother,
Ah,
she wouldn't let me do that.
Is that a thing for left-handed?
Oh, yeah.
I'm
I know a
left-handed.
bunch of, my brother actually does it.
I think it's older brother?
Like that.
Her
Older brother.
Okay. I'm
yeah,
left-handed.
because they're being taught by right-handed teachers who don't know how to teach a left-handed. This is back in the, well, my days, in the 60s.
And my mama said, my second son ain't gonna do that. My older brother still does that.
That,
I can't.
It hurts, it's like, it hurts to try.
You left-handed?
Yeah.
And you're
There's
left-handed?
three of them.
That's odd.
That's kind of rare.
all right. Questions to hear on anything that I just erased? Or talked about? Yes, Ken?
Could you talk a little bit more about the angular velocity direction? Because I'm still a little confused on. Because I saw your thumb, like when you were holding it, it looked like your thumb was pointing, I wanna say downwards, but.
All right, the direction is always going to be perpendicular to the rotation. So if it's rotating in a plane like this, the angular velocity has to be either up or down. It's perpendicular to this motion. So in the case, I know I flip my hand back and forth. So when it's spinning like this, yeah, my thumb's either gonna point up or down because this is rotating in a plane parallel to the ground. All right, good with that?
Yes.
All right. So think of this as the axis, and my fingers curl in the direction of the movement. So since the wheel is spinning around like that, the velocity is up. Angular velocity is up. If I spin it around like that, it's now curling around in that direction around the axis. The velocity is down.
Oh, okay, I get it more now.
It is actually, even though clockwise, counterclockwise is far more intuitive to people, in the long run, it does make more sense to be able to just identify it by a single direction. Right, any other questions? All right, so, well, you know, we don't have to do theory of the mind. It's gonna be exciting. Yeah, whoa. You need to go the other way. We flipped the direction of the angular velocity, right then and there, in front of you. Woo! We tell your grandkids.
Some of us can do that when we get home.
So what I want to know is the kinetic energy of the door. So for right now, we'll just assume that it's a rod from the sort of overhead point of view. And this thing is rotating around. I guess officially its angular velocity is into the board. Mass of the door, you know, I can take it off the hinges. Theoretically, or I could find the manufacturer and find out the mass of the door, or probably the weight, and then figure out what the mass is. So that's not a problem there, but what speed do we do for the door? Because this point right here is moving faster than this point right here. What would be an approximation? If you had to do a quick and dirty rough estimate, what would you choose for the mass of the door? Or sorry, for the speed of the door? Or what point on the door would you consider to be, you know, a reasonable approximation?
The middle?
Okay. So I could do the middle of the door, and I'll come up with an approximation for what the the speed is. It's a little bit off. As a matter of fact, the longer the door is, the more off it's gonna be. I can make it a little bit simpler, or a little bit more accurate if I pretend the door is two different pieces, and then I just do the center of this piece and the center of that piece, and I get something slightly better. So in that case, my kinetic energy would be 1/2 times basically m over 2, because I have two pieces, times, we'll call it speed 1 squared. Actually, we'll just call this mass 1 squared plus 1/2 mass 2 speed 2 squared. If I treat this as part 1 and part 2 of the door, it will be a more accurate estimate. It's still probably off. The longer the door is, the more farther off I am. Why stop at 2? Why not break it up into 4 pieces? In which case, 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared plus 1/2 m4 v4 squared. That's probably the last time I'm gonna write that out.
Ever.
Well, at least until I do this again. There's a shorthand notation. If I'm adding the same thing over and over again, there is a shorthand notation using the capital sigma. This is the uppercase sigma. And this just means sum. And here I write down what is the repeated bit. It's 1/2 times mass times speed squared, but I have different parts of it, so I put a little subscript here. I put the subscript I, because mass and speed change their numbers, and here I write I equals 1 to 4. This is just the shorthand notation of this. Because mathematicians, I hesitate to say lazy, they want to write efficiently. And so they want to find how few strokes of the pen do I need in order to express the idea. Notice that I could have also, since every term has a 1/2 in it, I could have factored 1/2 out. So this, I could have also written 1/2 times the sum m sub I v sub I squared, I equals 1 to 4. And then I can get even more efficient. The 1/2, 1 to 4, m sub I v sub I squared, and whatever the subscript is, that's what this letter represents, or that's what this number is. So you plug in the 1, plus, plug in the 2, plus, plug in the 3, plus, plug in the 4. Keep going until you get to that. In computer programming, it's a loop. All right, questions here about what this means or this notation? All right. Well, why stop at 4? Why not 8? Why not 100? Why not 1,000,000? If we break this door up into 1,000,000 different pieces, mathematically break it up into 1,000,000 different pieces, we'll get a really accurate estimate if you ever finish. Fortunately, there's a shortcut coming up ahead. So ultimately, I get an even more accurate if I think of this door as many pieces as possible. At the 1/2 m sub I v sub I squared, I equals 1 to, oh, what the heck, infinity. Why not break it up into an infinite number of pieces? This m sub I is the mass of each individual piece. So when it was 2 pieces, the mass m1 and m2 were just half the mass of the door. At this point, the mass is 1/4 of the door. At this point, what's the mass of each piece of that door?
An infinite amount.
Ooh, nope. Wrong direction.
Infinitely small.
Infinitely small. It's tiny, because you're taking the mass of the door and dividing it by a huge number. So we're basically doing an infinite sum of infinitesimally small things. That's what you do in Calc 2. But, don't worry, we got a shortcut coming up. Now, there is one thing in common for a rigid object. This is known as a rigid object because as you close the door, the whole door moves together. It's not like part of it moves and the rest of it catches up later. It's a rigid object. There is one thing in common to every part of that door. It all rotates with the same angular speed. Not the same linear speed, but the same angular speed. And we have done this before. What is the relationship between linear speed and angular speed? It would have been chapter 6. We were starting to deal with centripetal motion.
Speed is equal to the radius times the angular speed.
Yep. V equals omega r, or r omega, just like your move. So instead of writing V sub I here, I could just break it, just substitute omega r in for V. So my kinetic energy is 1/2 I equals 1 to infinity, m sub I, and then omega r sub I squared. Now omega doesn't have a subscript because omega is the same for everything. Just like that 1/2 was the same for every term here, we have an omega that's the same for every term. And so we can actually just factor that omega squared out. And so this becomes 1/2 omega squared. And what I'm left with is I equals 1 to infinity, m sub I, r sub I squared. And that's the shortcut right there. All of you are looking at that and no doubt going, my gosh, it's so simple. I'm going to step into the other room and grab the book and show you why that actually is a shortcut.
I would just like to take this moment to acknowledge that all of this is when the speed of the closing door.
But we're gonna do that.
All right. So this right here, this infinite sum of infinitesimally small pieces actually has a name, of course. This is the moment of inertia. Thus, our formula for the rotational, that we had 1/2 I omega squared for the rotational kinetic energy, it is just 1/2 mv squared, except we are taking into account that not everything is traveling at the same speed. That's all that the 1/2 I omega squared is. Now, the fact that I called it moment of inertia does not necessarily make you go, oh, yeah, now I got it. Page 330 of the textbook. Pretty much every beginning textbook has something like this. The black and white version. They'll have this table. This table has pre-done formulas. For those who have had calculus, this is just a quick aside. I guess for us, moment of inertia is this infinite sum of infinitesimally small pieces. And then the calculus aside, this would be the integral of r squared dm. If you don't understand what that means, don't worry about it. But this is solvable for common objects. And that's what they've done here, is they've basically gone through and they told you, hey, once you do that, this is what you get in the end. So, for example, just happen to have a ball right here. If I have a ball that's spinning about the center, the formula, once you crank through all of it, see, I'm assuming this is solid. This is for a solid sphere rotating about the center, about its center, 2/5 mr squared. Does Drupal capitalize them? Yes, they do. Typically, the notation is if I have a capital M and a capital R, I'm talking about the entire mass and I'm talking about the radius of the entire object, as opposed to the lowercase m and r, where I'm talking about to an individual tiny little bit in the ball. So using that, if I have this ball spinning, ball spins at 30 radians per second. Ball is, we'll give it a mass of 2 kilograms and a radius of 4 meters. This is a huge ball. The kinetic energy of the ball is 1/2 times the mass. So actually, do it step by step. And I'm gonna write it up higher because I'm tired of dropping down. It's rotating. So 1/2 I omega squared is the formula I'm using. I, for a solid sphere rotating about its center, is 2/5 mr squared, omega squared. So basically did a substitution there. And so this becomes 1/5 mr squared omega squared, which is 1/5 times 2 times 4 squared times 30 squared. Somewhere between, oh wait, then divide by 5. Somewhere around 60. Anybody actually, would someone be kind enough? $600 would be more like it than 60.
I got 5760.
57.
5760.
I got the same thing.
Yeah, 5,760.
All right, it's off by a couple orders of magnitude there.
60.
60. Units?
Yep.
Let's see if we can narrow that down some. You are right, there are units.
Joules?
Yes.
Units per kinetic energy?
It is joules. And it's spinning pretty fast at 30 radians per second, so that's about 5 revolutions a second. Ish. So 1,000 watts. I'm not even sure I'm getting up there. Questions up to here? Or we're about to take it to the next step. You now get beyond the box on ramp. It's all on ramp. And something will data. This time, so box on ramp, we can deal with friction with box on ramp, I have to give you the coefficient, because there's sliding going on there. Or if there's no friction at all, then it's just sliding. We've dealt with that one. Acceleration would be g sine theta if there's no friction at all. But now we're going to throw friction in, or we're going to go to the other extreme where there's no slipping at all. It will rotate, but it is not going to slip, which is a little bit unrealistic. There's always some slipping, thus you get in things like rolling friction. If I rolled a marble down the hallway, if I didn't give it much of a push, eventually the marble will stop. So, what are the forces acting on this thing? Well, we can be more specific than that.
Gravitational force.
Okay, or,
Weight.
yep. All right, so I got weight acting now.
Normal force.
Okay. But what other force involved?
You just said friction, right?
Yes.
Rotational.
Not just friction. Where's friction acting on the ball? Okay, up the ramp and at the point of contact. So my friction's acting right there. It is static friction. Because the ball is not sliding against the surface. It touches and goes from there. All right, so I have three forces acting on the ball, one of which is conservative, the other two are non-conservative. I'm not worried about the conservative, if it's the non-conservative ones that I care about. What is the work done by the normal force or the friction? Pick one, give an answer.
Normal force is gonna do the zero work because it's perpendicular to the movement, correct?
You would look at it that way. It is going to be zero. I think we're about to get into a subtlety to explain why there's a different way of looking at it, but it's still going to end up being zero. So the work done by the normal force is zero. 0 joules. Work done by friction. So you can come up with some height h and some length L. I don't know if that helps you at all. What is the work done by friction? What's the formula for work if you're stuck? Formula for work?
Changing kinetic energy.
That would be the total work. I'm looking for the more base formula. How would you calculate it?
Force over, force times distance. Or
Close,
The changing distance, or
closer. Well, there we go. Better, or actually spot on. Force times displacement. It's a dot product, which means it cares about how much of the force is in the direction of movement. So let's think about the movement of where the friction is acting. This point, right here, where the friction is acting, which way is that point going to move?
I'm sorry, say that again.
The friction is acting at this point on the ball at this moment in time. which way is that point going to move? Trying to think, up the ramp?
Opposite of the ball, like the direction of travel.
So as the ball's going that way, so it's going up the ramp?
Yes.
So you and Amaje are
Yes.
in sync. And Ian also in sync?
If it's rolling, I'm gonna agree, yeah.
Let's find out. Anyone else before we pull out the wheel? Or you wanna take a little bit longer, Brandon?
Are you looking for like the K and all of that, or no?
No, I mean, just pointing in the direction. I mean, up the ramp is an answer. But we're about to find out if that is actually a correct answer or not. I didn't know if someone wanted to chime in.
Sticking to it.
Let's take the point where the sticker is. Wheel's gonna go that way. Which way does that sticker move? Move backwards? Alright, so we'll put this tape, there we go, right behind it. So the wheel's gonna go that way. That sticker, you're claiming it's gonna move that way. Does not look like it. We center it better. That's, yeah, I'm definitely not seeing the sticker moving that way.
With the ball? With the wheel?
It's moving with the wheel, I will agree with that. But think again about which way this is moving.
It's moving in the positive direction.
Well, you can just make whatever direction it moves the positive direction, so, you mean that way?
Yes.
To the right. I don't know what else to say.
Actually, it's moving up.
Okay.
That's what I was looking at.
And that's a huge distinction. It's not moving to the right. Because notice that, first off, as soon as it moves, it's not touching the table anymore at that point. So friction's not acting anymore. Friction only acts on it while it's touching, and then it moves up. So that point on the wheel actually, or on a level ground, I guess, on this. It comes down, hits, and then comes back up, hits, and then comes back up. So there is a general tendency for it to move in the direction of the wheel, but not at that moment when the friction is acting on it. Therefore, the work done by friction is 0. Now back to Ian's comment about the motion being perpendicular to the normal force.